Hi everybody, welcome back to the section 3.1 video. In this video, we're going to take another look at an exponential decay model. And in this model, we're going to look at carbon dating. Okay, and we're going to take a look at carbon dating through an example of fossil age. So let's look at example 3. Let's go ahead and try and answer this question. So a fossilized bone is found to contain 0.1% of its original amount, carbon 14 or C14. And we're being asked to determine the age of the fossil. And here's a piece of material that will help us out is that the half-life of carbon 14 is 5,730 years. Okay, and we're being asked to use the following model. This looks familiar. Our exponential growth and decay model, dA over dt equals k times A, and an initial condition at time 0, a substance of A naught. So remember that the solution to an exponential growth and decay model is of this type. A of t equals the initial amount times e to the kt. Okay, so whenever we try to answer one of these questions, we always have to find out what k is. And it takes a little bit of work and a little bit of given conditions, but what makes it a lot easier here is that we're given what the half-life is. So note that the half-life is 5,730 years. So what we're going to do is use this and use our shortcut to make our work a little bit easier for this half-life. So using the shortcut that we previously discussed, that tau equals natural log of 1/2 over k, well, we can use our shortcut. Our half-life is this tau. So tau 5,730, which is our tau, equals natural log of 1/2 over k. So now we can just straight away find k. We can streamline the process. We multiply k to both sides. This becomes k times 5,730 equals natural log of 1/2. Divide that 5,000 to both sides. And so what we end up with is k is approximately, if you throw this in your calculator, negative 0.001, in the zero, sorry, 0.12097. Okay, so that is our k. So we streamline the process, less work than normally using this shortcut. It's a very handy shortcut to use when we're dealing with half-life. And so our solution, A of t equals A naught e to the negative 0.0001297 t. Okay, so that's not the final answer. We want to determine the age of the fossil after 0.01% of its original amount is contained still. So let's figure that out. Let's deduct that a bit. Since the fossil contains 0.1% of original carbon 14, we want to find t. We want to find the time t at 0.001 A naught. Where am I getting this 0.001 for? Well, 0.1 is a percentage, so 1, 2. So 0.001 times the initial amount left. So let's go ahead and figure this out. 0.001 A naught equals A naught, plugging this into our solution, e to negative 0.0001 to 0.097 t. And now we're just going to solve for t. So the A naughts cancel out. And remember, we raise each side to the natural log. So natural log of 0.001 equals natural log of e negative 0.0001 to 0.097 t. The natural log and e cancel out, and we're left with negative point, the decimal, and natural log 0.001 on the left-hand side. So we're just solving for t now. And we'll go ahead and take care of that as t is approximately 57,103.94. So therefore, the time or let's write it like this. We'll just say round it to 57,104 years is our answer. Okay, so the age of this fossil is 57,104 years at when is 0.01% remaining. So that's how you would do one of these problems, another decay problem, but in this situation, we were given the half-life already, and we use a shortcut to find our answer. So that's it for this problem, another decay problem. Thank you for watching, and I'll see you in the next video. Okay, take care.